Welcome back everybody to another video lecture. This video is going to discuss chemical bonding, and specifically this is going to cover sections 1 and 2 from your textbook, and those pages in your textbook are 175 to 189. So definitions of a chemical bond here: it's an attractive force between atoms or ions that binds together as a unit. So remember, the valence electrons of one atom are attracted to the nucleus of another atom, so this is what's going on. So here we have a picture of two atoms inside this little dot here. It's the nucleus on the inside, and then kind of imagine this is like the valence electrons of the element. So what happens is when we have a chemical bond, the nucleus is attracted to the valence electrons of another atom, and then the same thing, this nucleus is attracted to valence electrons of the other atom. And the reasons that atoms form bonds is that bonds tend to form because it decreases the potential energy or increases the stability of the atoms. So normally when atoms are just chilling in their space, they have high potential energies. And remember, nature always favors the lowest potential energy. So when atoms bond, they release energy and they have a decreased potential energy or increased stability. And the two types that we mostly are going to talk about are ionic and covalent bonds. So the first chemical bond that we're going to discuss is the ionic bond, and a good definition of this is where a cation is attracted to an anion. So here we have our sodium ion, and sodium here has one valence electron. So if we remember the octet rule, atoms are always striving to obtain noble gas configuration. So sodium has a choice of losing this one electron or gaining 7 more, so it would prefer to lose this one electron. So it's going to add it over here because chlorine has 7 valence electrons, and again it would be easier for chlorine to gain 1 electron than lose its 7. So what happens when sodium loses this electron is it has a positive charge, and so it becomes a sodium ion. Then when we have chlorine gains an electron, it has a negative charge. So it is also an ion. So we'd call the positive one a cation, the negative one an anion, and the attraction between them is an ionic bond. It's important to know that ionic compounds tend to form a crystal lattice. It's a highly ordered structure with a repeating pattern, and it's really stable. And the reason that it's really stable is because we have this kind of bonding between these positive and negative charges going on. So these big green structures here are chlorine, and our chlorines are, remember, going to tend to be negatively charged. And the small gray particles here are the sodium ions, and they're going to have a positive charge. So notice how many different bonds are forming between each atom. We have an attraction between these two. We have an attraction between these two, an attraction between these two, an attraction between these two. And because of all these attractions, it's going to give some specific properties to ionic compounds, such as high melting point and boiling point. And it's only because we have all these other attractions going on between different molecules. Another way to define an ionic compound is that its 2 or more elements are combined in a chemical bond by gaining or losing electrons that achieve the octet rule, or again, I always like to say the noble gas configuration. Now the next type of bond that we're going to talk about is a covalent bond, and this is a bond where atoms are sharing pairs of electrons between two atoms. So on the last few slides we were discussing the difference between ionic and covalent bonds. Remember that an ionic bond is where we have a transfer of electrons, and one atom becomes positively charged, which becomes a positive ion called a cation. The other one becomes a negatively charged ion, also known as an anion, and then that electrostatic attraction between them forms an ionic bond. The other type of bond that we're going to be discussing is this covalent bond, and so covalent bonds is where we're sharing electrons. Now covalent bonds can be categorized as polar covalent or non-polar covalent. And the way that we determine if it's a polar or a non-polar is we look at the electronegativity difference of the elements. And so here I have a rough sketch of the periodic table. I'm hoping you remember that electronegativity is highest up on this end of the periodic table. So actually this teal line kind of in the middle here kind of shows us, but it basically increases. So this is low electronegativity, high electronegativity here. So if I have two elements that, let's say, are like right here, right next to each other, they're going to have low electronegativity difference because they're right next to each other. So we would say that those would be nonpolar. Or also if I had the same element sharing electrons, so if we had bromine sharing with bromine, well, they have the same electronegativity, so there's no difference, so it's a nonpolar. On the other hand, if I had something over here like hydrogen, and then all the way over here, chlorine, if I had hydrogen and chlorine, I would definitely say that this is a polar bond because there is a high difference of electronegativity. If you look on the back of your printed periodic table, you're going to see a little chart that has electronegativity differences there, and so you can compare the electronegativity difference between hydrogen and chlorine and see that it's about 1. If we look at bromine and bromine, they're the same, so the difference in the electronegativity is 0. If you're still having a hard time distinguishing the difference between polar, nonpolar, and ionic bonds, you may want to refer to the polar bear cartoon comic that we read in class. And so the way that we tell the difference if something's going to be an ionic bond or a covalent bond is based off of the electronegativity. So it says here, using the electronegativity values, one can determine the percent of ionic character. And so depending on this percent ionic character, our bonds are going to be either nonpolar covalent, polar covalent, or ionic bonds. So if we have a nonpolar covalent, we have an equal sharing of electrons. So these bonds have a 0 to 3% ionic character, so that means it's very low ionic character. And one of the ways that we can calculate this is an electronegativity difference between 0 and 0.30. And if you look back on the back side of your periodic table that you're handed out in class, you have some of these electronegative values. So you can compare for yourself. Is it going to be a polar, nonpolar, a polar or an ionic bond? So the second kind of bond that we might see are these polar covalents. So we're still sharing electrons, but notice we have an unequal sharing now, so that's why we call them polar bonds. And these have between 5 and 50% ionic character. So they're still covalent because we're still sharing, but they definitely have an unequal sharing going on. And so we'll know that it's a polar covalent if we have electronegativity value differences between 0.3 and 1.7. On the other hand, if we have something between 1.7 and 3.3, so really pretty much as big as you can get here, so if your difference in electronegativity is 1.7 or bigger, we're definitely going to have an ionic bond. And this is a complete transfer of electrons, meaning that we have a 50% greater ionic capacity, and we already talked about these electronegativity differences. So if you're unsure on a test where something's going to be either an ionic bond or a covalent bond, remember, flip over to the back of your periodic table, check out the electronegativities of each element, make a comparison. If it's super small, it's going to be nonpolar. If there's a pretty good difference, it'll be polar covalent still, and if it's a giant difference, those two elements will form an ionic bond. Quick little definition here is a molecule is a nonmetal with another nonmetal. This is one of the things we discussed in our opening activity. And so a group of atoms are united by covalent bonds. So these bonds, again, can be polar or nonpolar covalent. So here we have ammonia. In the center here is our nitrogen and our 3 hydrogens. Here we have chlorine. And notice it's 2 chlorine atoms that are put together, and this is often described as a diatomic molecule. And so this would be a classic example of a non-polar covalent bond because chlorine atoms, they're the same, so they're going to have the exact same electronegativity. So this might have an electronegativity of 1, this has an electronegativity of 1, but the difference between them is 0, so that's how we know it's a non-polar covalent bond. On the other hand, if we look at water, we know that these hydrogen atoms here have really low electronegativity, and we know that oxygen here in this red, it's kind of hard to see with the laser pointer, but the idea is that oxygen is an electron hog, and so it's going to be pulling the electrons away more from the hydrogens. I think we did that polar bear penguin example thing in class. So remember, oxygen is your polar bear stealing the ice cream cones from the little tiny penguins here. So this would be an example of a polar covalent bond. So another definition here are just molecular substances, and these are substances that are made of molecules. And remember, molecules are made of covalent bonds. So we have the law of octet here, or the octet rule. So atoms tend to gain, lose, or share electrons in order to get a full set of valence electrons. And again, this is usually 8, but for example, hydrogen's looking to have 2, helium already has 2, and then we've got beryllium and a few others that want different numbers of electrons. So here we have the Lewis structures. We've drawn the singular Lewis structures in class, the Lewis dot structures for each element, but now these Lewis dot diagrams, the objective here is to gain those 8 electrons. So here we can see oxygen in black, and you can see the 6 electrons around oxygen. But notice that oxygen only has 6 electrons, so it's looking to get 2 more electrons, and so it can get the 2 more by attracting these hydrogens, and each hydrogen brings its own electron. So when they form water, we have now a full valence shell for oxygen, so we have 8, but we also have a full valence shell for hydrogen here, because remember, hydrogen only needs 2 electrons. And up here we have an example. Again, chlorine is looking to have 8 valence electrons. Each chlorine has 7, so each one is going to donate one of these electrons here in the center. And we'll do, or we should have already done, lots of practice on how to write these Lewis dot structures in class. So remember that these Lewis dot structures are just showing the valence electrons in compounds, showing how each atom is satisfying the octet rule. So another way that we can show these sharing of electrons in Lewis dot structures is by writing lines in between each of the atoms, and it's just a shorthand way to write this. So a line is going to equal 2 electrons. So 2 shared electrons make a covalent bond, and lines show the bond between the atoms in the compound. So remember a second ago we had 2 electrons here and 2 electrons here, but now instead of doing the dots, we'll just draw the single line indicating that they're sharing that pair of electrons. And again, here we had 2 electrons a second ago, now we've just drawn a line in between indicating that the atoms are sharing that pair of electrons. So now we're going to go ahead and discuss a strategy and how we can draw Lewis dot structures of compounds. And the strategy we're going to use is something called NASU. And so what we're going to do is we're going to start off by finding out the total number of valence electrons that are needed. Most of the time atoms are requiring 8 if you refer to the octet rule, but hydrogen only requires 2 because it only has that 1 energy level to fill. The next thing we need to know is how many are available. So what we're going to do is we're going to count up the number of valence electrons each atom brings. The next thing we're going to look at is the number of shared electrons that we're going to find in the compound. And we determine the number of shared by taking the needed minus the available, and that will give us our shared. S stands for shared. And then the last thing we need to do is find out how many electrons are going to be unshared, and that stands for U, unshared. And we're going to take the available minus the shared to figure this number out. So the basic rule here is that you take the atom that has the lowest electronegativity and place it in the center. So place a single atom in the middle. The other atoms are around it. You want to try to make it as symmetrical as possible. And then we're going to place the electrons between them, the shared, to try to get the octet rule. Now, if you're completely confused right now, don't stress. We're going to have an example on the next slide. So the example that we're going to use here is methane. So methane's chemical formula is CH4, 1 carbon and 4 hydrogens. So the first step is to find the amount needed, or the number of electrons that are needed. So we have 1 carbon, and carbon's going to need 8. Then we have 4 hydrogen, and remember hydrogen's only looking for 2. So when we add this up, 8 plus 8 gives us 16 electrons needed. Then the next step is to find the total of electrons that are available. So carbon has 6 electrons, it does, but it only has 4 valence electrons. So remember, we only use our valence electron number here. And again, we have 4 hydrogens, and each hydrogen brings to the table 1 electron. So 4 plus 4 is 8. So there's 8 electrons that are available. Now we need to figure out how many electrons are going to be shared and how many are going to be unshared in our Lewis structure. So to find our number shared, we take our needed number minus our available number. So remember, we needed 16 electrons and 8 of them were available. So this means that there's going to be 8 shared electrons. Then to find our available, we take to find our unshared, we take our available minus our shared, so 8 minus 8 is 0. So in our structure here, we're not going to have any dots. We're not going to have any unshared pairs of electrons. All we're going to see are lines or shared pairs of electrons. So we place the single atom in the middle. We place the other atoms around it. So we put carbon and then we put the hydrogens. And then it said that there were going to be 8 shared electrons. So remember, in each line is representing 2 electrons. So we only have 4 lines or 4 bonds because this is 2, 4, 6, 8 shared electrons, and that's only 4 bonds. So we place the electrons based on the shared. We didn't have any unshared electrons, and so you're done with your structure. So this is what our Lewis structure for methane would look like. So let's do another example here with ammonia. So remember, step number 1, determine the need. Step number 2, determine the available. Then determine the shared for step 3. And step 4, determine the unshared. So let's go ahead and figure this out. So how many are we going to need? So nitrogen is going to need, so let's do N for need. Nitrogen is going to need 8. And then we have 3 hydrogens, and each hydrogen is going to need 2. So 8 plus 6 is going to be 14 electrons are needed. Next, we're going to find our available. So nitrogen brings 5 valence electrons to the table. Again, we have 3 hydrogens, and each hydrogen brings 1 valence electron. So then 5 plus 3 is 8, and this is how many electrons we have available. Now let's figure out how many are going to be shared. So what you're going to do is you're going to take your needed minus your available. So I'm going to go 14 minus 8 equals 6. So I know I'm going to have 6 shared electrons, or we might also think of this as having 3 bonds or lines drawn in our structure. Then let's look at our unshared. So I'm going to take 8. So we're taking now our available minus our shared. So 8 minus 6 equals 2. So I should see 1 lone pair electrons, 2 electron dots around our structure. So remember, we want our molecules to look as symmetrical as possible. That's one of the easy ways to create the right Lewis dot structure. So we're going to put nitrogen in the middle because it's the only singular atom, and then we're going to distribute the hydrogens equally around the nitrogen. So here on this slide, we're going to go ahead and see how we would draw the Lewis structure for ammonia here. So remember, we're going to put nitrogen in the center. We're going to put the hydrogens around to make it symmetrical. Then each hydrogen only needs 2 electrons to be satisfied, while the hydrogen is going to need 8 electrons. So we first looked and we see that there's going to be 6 shared electrons. So I'm going to put 1, 2, so hydrogen's happy. 1, 2, now this hydrogen's happy. This hydrogen is now happy. And so there's our 6 shared electrons. And in just a second, we're going to be able to draw these lines like this for it, because remember, 2 electrons is represented in each line here, or each bond. Now we have 2 unshared pairs of electrons, 2 unshared electrons that we need to put, and nitrogen, look, it only has 6 valence electrons, so now it needs to have 2 more, and now nitrogen is going to be satisfied. So the way that this is going to look when we're done drawing it is our nitrogen with a hydrogen, another hydrogen, another hydrogen, and so there you can see our 6 shared electrons and our 2 unshared pairs of electrons. Okay, so the last example that we're going to do here is for formaldehyde, and I know the top of the slide here is cut off. So this is the formula for formaldehyde here. It's CH2O, and so remember, for step 1 we need to figure out the number that we need, so the needed. So we have 2 times 8, and the reason we have 2 is because we've got carbon needs 8 and oxygen needs 8, so there's 2 items that need oxygen. And so 2 times 8 because it's carbon and oxygen, and then we have 2 times 2 because we have 2 hydrogens, and each hydrogen requires 2 electrons. So the total here, 16 plus 4 is 20. The next step is how many is available, and so carbon, there's 1 carbon, and it brings 4 valence electrons. Then we have 1 oxygen, and it brings 6 valence electrons. then we have 2 hydrogens, and each hydrogen brings 1 electron. So when we add this up, and let me just say this is for carbon, this is for oxygen, and this is for the hydrogens. This equals 12 that are available. So remember, the way that we calculate the shared is we take the needed minus the available, and this equals our shared. So we've got 20 minus 12, and that gives us 8 that are going to be shared. And so just in my thinking, I'm thinking, okay, I'm going to have 4 bonds here. And then the unshared we calculate by taking the available minus the shared. This gives us the unshared, so we took 12 minus 8 equals 4. So we're going to have 4 dots around our structure. Now here on this slide, it's asking you, would you have guessed whether carbon or oxygen goes in the middle? And we're going to say on this slide that it's carbon goes in the middle because it can form the most bonds. But also the thing to think about is which is the least electronegative. Carbon is less electronegative than oxygen, and so that kind of rule still applies, that whatever the least electronegative goes in the center here. So then it says the bonds go between the atoms, so each bond uses up 2 electrons, remember, and so we needed to have, I believe it was 8, but so we only put the bonds in here that we can see. So there's only 6 electrons being used in our bonds, so we're like, hey, what's up with that? So the way that we solve this problem is we look at our shared electrons, and so we only shared 6 of our electrons, and we needed 8, so there's 1, 2, 3 bonds. So we're going to need another bond, and we know that carbon can use some more electrons and oxygen. So what we're going to do is we're going to add a double bond, so we're going to add another bond here, and that'll take care of those 2 electrons. Now carbon is satisfied because it has its 8 electrons surrounding it. Hydrogen is satisfied because each one has 2 electrons, but oxygen is still not satisfied. Well, luckily we still have these 4 unshared pairs of electrons, so I'm just going to place 1, 2, 3, 4. Now oxygen has 8 electrons around it, so it satisfies the octet rule. So another way that we could draw this would be carbon, 2 electrons for each hydrogen, then the 2 shared pairs of electrons here, oxygen, and then the lone pairs on the outside here. So often we'll see double bonds occur in oxygen and carbon dioxide. So let me go ahead and draw the Lewis dot structure and then the more simplified version of oxygen. So oxygen, remember, it brings 6 electrons to the table, and so what we would do is we'd place those 2 paired shares of electrons here. Each oxygen would have, again, 2 lone pair. And so if we were to count this up, notice that oxygen has 8 electrons around it. This oxygen has 8 electrons around it, so each oxygen is satisfied. A quicker or shorter hand way to draw this would be oxygen, the double bonds, and then with the valence electrons. And sometimes you might notice that chemists don't even draw these valence electrons after a while. The other one is carbon dioxide. So carbon would be in the middle. Oxygen would be on the outside here. Put our valence electrons in for each oxygen. Now if we were to count around carbon, carbon's got 8 electrons. Each oxygen has 8, so it's satisfied, so we know we're drawing the correct structure. On the other hand, nitrogen forms triple bonds, and that's because nitrogen normally has 5 valence electrons, right? And so it's looking to form 3 more bonds, so it will do a triple bond, and then it only has 6 electrons each, so each nitrogen is going to need to have 2 pairs of valence electrons here. So if you were to count up how many were available, you would see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and each nitrogen brought 5 electrons to the table to share, so for a total of 10 electrons, and that's what you can see in our structure. Now there are some structures that cannot be drawn correctly with just a simple Lewis dot structure diagram. The actual structure is an average of all the possibilities. So we show these possibilities with this idea of a double-headed arrow here. So for example, here we have ozone, and remember that is a substance in the atmosphere that stops UV radiation from getting to the surface. And so ozone, 3 oxygens, can be like this with a double bond here. But sometimes if you look at it, the double bond's here, and so it kind of rotates back and forth, this pair of electrons. So it's not like we can just draw one of these and say this is the correct structure, because the electrons are rotating back and forth. So we use this double-headed arrow, and this is called a resonance structure.